Hi, I'm Professor David Farina. In today's lecture, we're going to be talking about light and matter and how it's connected to the inner workings of our cosmos, specifically the electromagnetic spectrum. Let's get started. Charged particles are a very important concept to understand when it comes to electromagnetism. Now, the word electromagnetism is a big hint. The electric fields that are produced by charged particles do play a major role in how an electromagnetic wave is formed. So let's break this down in order to get started. First, whenever we have a charged particle in space, it is producing electric field lines in all directions. Those field lines can interact with distant charges, and the amount of interaction has an important role in the distance between those particles. So the larger the distance, the less the interaction is occurring. When we vibrate one of these particles, we can produce a wave. Electromagnetic waves are also very similar to what we connect to our normal magnetic fields. In a magnetic field, like the magnetic field of the Earth, we have magnetic field lines that are coming out of the South Pole. This is the same as in a bar magnet. So they come out of the South Pole, travel around, and go into the North Pole. When we have a concentration of magnetic field lines or electric field lines, we end up with a higher and more powerful electromagnetic field. Now, how are these two things related? In one orientation, we have the electric field. In a perpendicular direction, we have the magnetic field. And I really like this little simulation up at the top here. So we have the electric field being produced kind of on the plane of the monitor, and then we have going in and out of the monitor in green, the magnetic field. Electromagnetic waves cannot be separated. This is something that was determined early on in the 1900s, and Albert Einstein played a major role in the connection of these two separate forces of nature. We thought they were separate, at least, up until the early 1900s. So now we know that electromagnetism is one force and that it works together always. In an electromagnetic wave, these waves travel at a rate of 3.0 times 10 to the 8th meters per second in a vacuum. That's the speed of light. It's the speed limit of our cosmos. To give you a little better perspective, this is 7 times around the Earth, or about 7.5 times around the Earth in a single second. It takes about 3 light seconds to get to the moon. It takes about 8 light minutes to get to our sun. And for distant places in the solar system, like Mars, it'll take upwards of 45 minutes. And the deepest places in our solar system, upwards of hours. And then, of course, stars, it may take many years or many hundreds or even thousands of years to get to local stars. And then other galaxies are upwards of millions and even billions of light years away. Electromagnetic radiation comes in many different types. You're most familiar with the visible spectrum. The visible spectrum of light is what your eyes can see. And it comes in the following colors, the same as the rainbow: red, orange, yellow, green, blue, and violet. These colors of light are always in this exact same order, with the red side of the spectrum being the longer wavelength light with the lower energy, whereas the violet side of the spectrum is a shorter wavelength and a higher energy. Now, on either side of the visible spectrum, we have infrared, which is inferior to red, infra, and we have above violet, we have ultra, or beyond violet. So we've got the infrared and the ultraviolet, which are on either side of red and violet. Now, at the lowest of energies and the longest of wavelengths, we have the radio waves. In the opposite direction, we have X-rays, which are going to have higher energy than the ultraviolet, but less than the gamma radiation. These also will have a very short wavelength, a very high frequency. Okay, and the gamma radiation is by far the most energetic. It has the shortest wavelength and the highest frequency of all of the electromagnetic spectrum. So when you're looking at this, it's important to notice and understand that frequency is going to increase, starting with radio waves being the lowest frequency. It's going to increase as we go towards gamma. And when we talk about wavelength, we're going to have the longest wavelengths here on the radio side and the shortest wavelengths on the side of the gamma spectrum. This also plays a role in the penetration power. And what I mean by that is its ability to move through matter. So gamma radiation, of course, can go right through matter and out the other side. X-rays, you of course are aware, we can use this for medical purposes to look straight through your skin and be able to see your bones. And so this is pretty highly penetrating. Ultraviolet is also highly penetrating on your skin level, and that's why we need to be very careful when we're out in the sun. UVA and UVB are what you might see on a sunblock. These are the same UV or ultraviolet that we're talking about here, and what ends up happening is the ultraviolet rays penetrate your skin and can damage your DNA, causing cancer. Other than just a sunburn, the ultraviolet effects can be cancer causing. So be very careful when you're out in the sun to put on sunscreen or protect yourself with covered clothing. On the opposite side of things, infrared you might see used for things like a remote control for a television. So that's a pretty interesting experiment. Try this by putting it up to your cell phone camera. If you have an Android phone, use a remote control and just click away at it. If you have an old webcam or your computer's webcam, that works too. iPhones do have a blocking filter on it, so you won't be able to use it with Apple devices. I'm not sure about I know it won't work with an iPad either. I'm not sure about their computers, but give it a shot. The electromagnetic spectrum on this picture is given to you with some other important scale values. So radio waves can be like the size of a mountain. Here's Mount Everest, for example, or a skyscraper, down to, maybe humans or a fingernail on the higher frequency microwaves. We move into the infrared. We're looking at a wavelength that's about the size of a head of a pin or dust particles. As we move into the visible light spectrum, we're talking about bacteria sized. So these are microscopic, beyond your vision. As we get into the near ultraviolet and far ultraviolet, we get down to the size of a virus, very, very tiny. As we move into the X-rays, we're talking about an atom-sized wavelength of the particles. And then as we get down to gamma radiation, we're talking about something the size of the atomic nucleus. So hopefully this scale gives you some ability to get a handle on the scale of these waves and their sizes. Check out this link here with the NASA electromagnetic spectrum. If you're interested, I'll put a link in the comments below. So this is actually a picture from that NASA website. I just wanted to zoom in on this so you'll see the atmospheric windows here. So there are two main atmospheric windows. And what I mean by that is the ability for these waves to penetrate the Earth's atmosphere. The first type is the radio waves. They're capable, and so is, of course, visible light. Now, there are places in the atmosphere where there are some dips that don't quite make it to the surface, but if you have a high enough mountain peak, or if you fly a jet up in these regions, higher up in altitude, so this black line, for instance, would be the ground surface at sea level. So you're seeing visible light spectrum. Some of the infrared is able to also make it to the surface. Radio waves here, but nothing else. Importantly, nothing else makes it to the ground level. So if we're trying to observe outer space in any other wavelength of light, we need to actually use space-based telescopes in order to view what's going on up there. So if you want to look at things in the gamma spectrum or the X-ray spectrum, in most of the ultraviolet, many parts of the infrared, and parts of the microwave or the far parts of the radio spectrum, you do need to go into outer space. It's also important to note that the scale that we're using here is a logarithmic scale, and what we mean by that is it's on powers of 10. So just be very careful when you're reading these scales that you're taking that into account. So thank you very much for watching our lecture today on the electromagnetic spectrum. I hope you learned something. If you did, please click like and subscribe at the bottom so that you are able to find out when I'm making my next video. Thanks a lot, and have a great rest of your day.